Hello students, in this video we'll find an inverse Laplace transform that is represented by a Fourier Sine Series. Let's consider the function that has this Laplace transform, 1 over s squared minus 1 over s sinh s, okay? Let's find f of t such that Laplace transform of f of t of s is given by this function over here, f tilde of s, okay? We can use the Bromwich integral formula, right? So we need to find all the singularities, right? So to use the Bromwich integral to find the inverse transform, we need to find all the singularities of this function. Of f tilde. Okay, so what are the singularities? You might look and say, oh, 0 is a singularity of this function. It's not, right? How do I know that so quickly? I know it so quickly because sinh of s near the origin looks like s, right? So this looks like 1 over s squared minus 1 over s squared. The singularities can cancel out there. So in other words, s equals 0 is a removable singularity. So note, s equals 0 is a removable singularity, so there's no residue to compute there. So there's no residue, right? Okay. The other singularities occur where? The other singularities are going to occur at the roots of sinh, right? So the other singularities are the roots of sinh. Okay, and where do those singularities happen? Those singularities happen near what point? Near the point, at the points what? At the points, let's see, that's gonna be like the multiples of pi, right? So hence s is plus or minus, let's take Sn to be n pi, and Sn bar to be n negative n pi, where here n goes from 1 to, and so on. So there we have our singular points, right? And so now what's the idea? The idea now is that to compute these singularities, what do you do? So what's happening over here is that we have something that's exactly of the right form that we want, right? So what we're going to say is therefore f of t is going to be the sum, n goes from 1 to infinity. Since I know the structure of these poles, it's going to be twice. And of course, these are multiplied by I, right? Because I put sinh instead of sine. Twice the real part, we've seen this from previous videos, of e to the I n pi t, like that. Good. And then we're going to have what? Times the coefficients over here, since they're all simple poles, right? They're going to be simple poles, times b1n, right? Where b1n is exactly going to be the coefficient of 1 over s minus in pi in the Laurent expansion. Okay, so you figure that out now? Good. And of course, we're using the fact, we've already proven this several times already, we're using the fact that these are simple poles, and then I can just use the fact that the poles occur in complex conjugate pairs, and then I add those together. These are purely imaginary. There's no real parts, so there's no prefactor of e to the t over here. They're just purely imaginary. So we have this e to the I n t, that's the imaginary part, right? That's my e to the I beta t, and then I just have to do the principal part of those expansions. Good, so let's do it. Okay. So how should we do this over here? Well, let's simplify this a little bit. So if we simplify our expression, our f tilde of s is what? Our f tilde of s is going to be, let's think, it's going to be s sinh s minus s squared, all divided by s cubed sinh S, okay? So this has the form that we want as a form of a P of S over Q of S, and so now I can immediately find out what those residues are, the principal parts, right? So in other words, what this tells me is this allows me to compute that the residue, these numbers B1n, are exactly just equal to the top function, S times sinh of S minus S squared, evaluated at S equals Sn, these numbers over here, Sn, over d by ds of S cubed sinh of S at what? At S equals Sn. So let's do that. Let's figure out what this is going to give us over here. So of course, if I plug the Sn into the sinh over here, they're going to vanish because those are the roots of sinh, right? So those are the roots of sinh, so those terms are going to be gone. So we're going to have 0 minus Sn squared, all divided by what? All divided by d by ds is going to be two terms over here. It's going to be an S cubed sinh, so S cubed sinh, S cubed Sn sinh of Sn. Those are going to be gone. And then 3 over here, so then plus 3 Sn squared. And then what? And then cosh of S, no, I had that wrong. So let's be careful about this. So that's where things are going to cancel out for us. So let's be careful. I did the derivative wrong. Let's do this carefully. So what's going to happen over here? So we're going to have, it's going to be S cubed, Sn cubed, times the cosh, right? Cosh of Sn, and then plus 3 Sn squared sinh of Sn, but those are going to be gone, right? The sinh of Sn are 0. Now what's the cosh of Sn? Well, the cosh of Sn is the cosine of Sn, and the cosine of these things is going to be -1 to the n, right? So -1 to the n, the cosine of those things is going to be -1 to the n, so this is going to be negative Sn squared over Sn cubed times -1 to the n. So that's going to give me a what? That's going to give me a -1 to the n plus 1 over Sn, like that. Excellent, okay? Okay, so now we're in our position. So what is twice the real part? So now what's the real part? The real part of e to the I n t times these things, e to the I n pi t, times -1 to the n, -1 to the n plus 1 over Sn is going to be a what? Is going to be a factor of, let's see. So my Sn is going to be I n pi. So I have an I n pi like this. Great. And so now we're in good shape. Because what can I say? I can now say that this thing over here is exactly equal to what? So this is the real part. Now that's the same thing as -1. So I can take this I and put this in the numerator, and that's going to give me a what? So this is going to be a, this thing over here is what? This thing over here is cosine of n pi t plus I sine of n pi t, right? And so that I is going to cancel out here and here, and so this is just going to be the real part. That's not going to care about. The real part is just going to give me a what? Now, the I is going to hit the cosine, right? So I'm just going to have the real part of -1 to the n plus 1, and then just sine of n pi t over n pi. Beautiful. And so now, this is real, so that we can just cancel out the real part, and we just get that. Excellent. So now we have what we want, and then we have two of these things over here. So now, we have this expression. Good. And so therefore, our f of t is what? Our f of t that we're looking for, our f of t, is going to be the sum. N goes from 1 to infinity. And then I'm going to have a negative, I'm going to have a 2 over n pi, -1 to the n plus 1, sine of n pi t. And so we've just represented f as a Fourier sine series by using these Bromwich integrals. Beautiful. So we've seen now examples of Bromwich integrals giving Fourier cosine series, Bromwich integrals giving Fourier sine series. So now we can really start to believe the fact that these things are intimately connected with PDEs on finite domains, which we'll address in further videos. Thank you very much.